Welcome to The Explainer. Today we're diving into a photographic technique that is, well, it's pretty mind-bending. It lets us capture things that are literally invisible. I'm talking about stuff like heat, sound, even the shockwave from a speeding bullet. So how is that even possible? Let's find out.
All right, let's just jump right in. What you are looking at right now, it's a real photograph. Seriously, this isn't CGI, it's not some kind of simulation. That is an actual bullet flying faster than the speed of sound. And those ghostly lines that you see wrapping around it, those are the shock waves. That is literally the sound it's making as it just tears through the air.
And, yeah, that's the big question, right? How do you do that? We can't see sound waves. We can't see the heat shimmering off a candle or tiny little changes in air pressure. So how on earth can a camera capture any of it? Well, the answer comes down to taking advantage of a really simple but totally brilliant property of light. Okay, section 1, when light bends. To get our heads around this, we've got to kind of rethink something we take for granted, that light always travels in a perfectly straight line. Turns out, its path can be bent. And that bending, that's the whole secret.
You know, think about a simple shadow. We see it as having this sharp, clean edge, right? But it doesn't. If you could zoom way in, you'd see the light doesn't just stop. It actually bends a little bit. It diffracts right around the edge of the object. And that tells us something super important. The path of light is not as rigid as we think.
This bending has a name. It's called refraction. And you've seen this a million times. It's why a straw in a glass of water looks like it's broken at the surface. See, light travels at one speed through the air, and then a different speed through the water, so it bends. And here's the cool part. The exact same thing happens when light travels through air that has different temperatures or pressures, because all of those things change the air's density. So picture this. Imagine a bunch of perfectly parallel rays of light, just streaming through a room where the air is totally still, totally uniform. Just as you'd guess, they're all going to travel in perfectly straight lines, right next to each other. No drama. Okay, but now let's throw in a little change, a gentle, smooth change in the air's density. Think of it like a wedge of slightly warmer air. Because that change is really consistent, all the light rays bend together and by the exact same amount. So they stay parallel, they're just on a slightly different path now. But what if the changes in density are messy, chaotic, like the turbulent hot air rising off a candle flame or the crazy compression of air from a shockwave? Well, now those light rays get bent all over the place. Those nice parallel lines become a complete, jumbled, distorted mess. And that distortion, that's the signal. That's what we're looking for.
And believe it or not, this isn't some brand new idea. People have been noticing these little distortions for centuries. Way back in the 1600s, this guy, Francesco Grimaldi, he actually wrote down and recorded these weird, faint patterns he was seeing inside of shadows. He had no idea what was causing them, but he knew he was seeing something that just didn't fit with the simple idea of light always traveling in straight lines.
Section 2, the knife edge trick. Okay, so we've established that invisible things can bend light, but how do we actually see that bending? How do you take that subtle, jumbled mess of light and turn it into a clear, sharp picture? Well, the answer is this incredibly clever, but also surprisingly simple optical trick. So this is the setup that pulls it off. It's called a Schlieren system. Here's how it works in a nutshell. First, you take a light source and use a mirror to spread it out into a big beam of parallel rays. Then that beam passes through what we call the test area. That's where the invisible event, like the shockwave, is happening. After that, a second mirror collects all of that light and focuses it all the way back down to one tiny, super bright point. And it's right there, at that single point, where the real magic happens.
This is the secret sauce. At that tiny little focal point, you put a razor blade. They call it a knife edge, and you position it so it blocks about half of that focused light. Now think about this for a second. The light that wasn't bent at all, it gets partially sliced off by the blade. But, and this is the key, the light rays that were bent by, say, a heat plume or a shockwave, they're now traveling on a slightly different path, so they might miss the razor blade completely, or they might get blocked when they otherwise would have passed through. It's this simple move that turns those tiny, invisible bends of light into dramatic, bright, and dark areas that a camera can finally see.
Section 3. Seeing heat and shockwaves. All right, so now we have our tool. We can separate the bent light from the unbent light. And with that, we can suddenly see a whole world of things that were totally invisible just moments ago.
And the difference is it's stunning. I mean, with this setup, a simple candle flame isn't just a flame anymore. It's revealed to be the source of this enormous turbulent column of hot air rising above it. The invisible heat coming off your own hand becomes this visible, ghostly plume. You can even see the shockwave from a simple hand clap expanding out into the air. It's wild.
And check this out. This really shows you how powerful this technique is for scientists and engineers. What we're looking at here is an object inside a supersonic wind tunnel. And those sharp, dark lines you see, those are the incredibly intense shockwaves that form as air is forced to flow over that object faster than the speed of sound. This is literally how you visualize the aerodynamics to design things like supersonic jets.
But here's where things get really next level. This technique isn't just for making cool pictures. It's for generating hard scientific data. These images are actually maps. So on the left, you see the shockwave from a small explosion. Now that white line is just a slice taken right through it. The graph on the right, that's showing the exact brightness of every single pixel along that line. And you can see the light and dark spots aren't random at all. They correspond perfectly to exactly how much the light was bent at every single point.
And because physics is, consistent, scientists can actually work backwards from that information. There's a known physical constant, think of it like a conversion factor, that creates a direct link between how much the light bends and the actual density of the air. So they can take the brightness values from the picture and start calculating the real physical properties of the air in that shockwave. And this is the final, absolutely incredible leap. The brightness of 1 pixel tells you how much the light bent. That, in turn, tells you the density of the air at that one tiny spot. And once you know the density, you can calculate the pressure and even the temperature inside that explosion. All of a sudden, a photograph has become a super detailed remote thermometer and a pressure gauge, mapping out an entire event without a single physical sensor ever having to touch it. It's amazing.
Section 4. A hidden world revealed. So, after all this incredible physics and clever engineering, what's the big takeaway here?
What it really shows us is that our world is just pulsing with these invisible forces. The air around us isn't empty. It's this dynamic, living medium, and it's filled with the heat coming off our skin, the turbulence from our breath, the sound of our voices. And with a surprisingly simple tool, it's just mirrors and a razor blade, we can actually get light to show us this hidden reality that is happening all around us all the time.
And that really leaves us with one last thing to think about, doesn't it? This technique, Schlieren imaging, it reveals a layer of physics that we knew existed, but we just couldn't see. It really makes you wonder, what else are we looking at every single day but just completely failing to see? What other secrets are hiding right there, in plain sight, just waiting for someone to find a clever new way to look?